I will show a little bit more about where to apply it, and especially how to apply in the circuits where we also have superconducting quantum circuits, quantum bits. But before that, I think I want to finish off with some few things. I think it takes like 10-15 minutes about this more or less classical part of the story. So I promised yesterday that I will also explain you about another type of a Maxwell demon. Probably I will not go now into the details. You can find the thing described in this paper, and there's a review also about this experiment later. But the idea was, I was explaining yesterday that the powers that we obtain with this demon, which is really controlled from outside your setup, are extremely small. So they are unmeasurably small. But so there has been some kind of a idea and guest of finding realizations where you could really measure the work or the heat directly in these systems, and that's where something called a autonomous Maxwell's demon comes into a play. Oh, hello, and this circuit is shown here schematically. So it's kind of all in one. So you remember we had a system which was controlled from outside. The state was measured, and then there was a feedback on the time scales of second. So now what we have here is a system, and it is directly coupled to another system which now acts like a Maxwell demon for the first one. And they are coupled capacitively, so there is Coulomb repulsion that acts on the top circuit. So in this circuit, the general idea is that it is a coupled system, capacitively coupled system, whose Hamiltonian, which is just the charging part, because we are dealing with normal circuits, is shown here. So there's a charging of this top part, which we call the system. Then there's charging of this lower part, which is a demon, and then there's coupling, with this J comes from the capacitance and the other capacitances in the circuit. So in principle, you can, if you drive it to by the control parameter Ng, small and capital Ng, to the degenerate points, so that these have a value, half integer value here, then it doesn't matter which charge state the system has for these internal energies here, but it influences the coupling between the two. So there's a Coulomb repulsion. And then it's possible to realize a cycle which is shown schematically here. So so the system is a Coulomb blockaded SET. So if you bias it slightly and you have the gate voltage such that it costs energy for the electron to tunnel onto this dot, then when this happens due to the coupling to the heat bath, so there's thermal energy that drives the system in the preferred direction. When this happens, then both these electrodes are to be, or this electrode here is cooling down. So, but if you have this coupling, repulsive coupling between these two, then the demon part, which is single electron box here, reacts quickly if this transparency of this contact here is low enough. So then what happens is that there's a tunneling out of this system here, that the potential in the SCT drops, and again this electron sees like a cost of energy to tunnel out. So in the next phase of this cycle, this electron, when it tunnels out, it again needs to take energy from the bath, and when this again occurs, due to this Coulomb energy here, the demon part restores the initial state, so that it comes back, the electron comes back to the dot. And this is something that runs cyclically, so it's totally autonomous. You don't have to do anything except have a small bias on, and the system is running. So in the experimental realization, what we did was that we attached thermometers to different parts of the circuit. So this is really the system part here. It's fairly complicated structure, as you see from the fabrication point of view. And there's a thermometer here, a regular NIS thermometer, as we discussed yesterday, on the right side also. And then also the detector, or the demon, which is here, its temperature can also be measured by a similar thermometer. And we use the standard NIS thermometers to do this. So now one can, indeed I will not go to any deep detail of this, but one can really look at the different the operation of the system as a function of the two different gate voltages. So I repeat that the favorable demon operation is when you can ignore the energies of these internal energies of the two SCTs, and only the coupling part remains when you have a half integer value of the gate voltage here. So if you're not in that position, then you can assume that that this demon is idle. It does not react if you are far from this thing, because the charging energy of this lower part is large enough. And then you cannot really achieve cooling of the whole system, of the top system as such. But if you come to the favorable position, then what one can see is that this top island in this system, due to this expensive tunneling events, is cooling down, or both ends of this system are cooling down. So the whole system is cooling down thanks to this to this demon operation. And one can of course analyze this with the mutual information as well. So there's no direct heat transport between the two. There's only this Coulomb repulsion which controls the system. Okay, and this can run very fast, so we can the cycle is at the frequency of several megahertz, which means that then the powers, yesterday I wrote this down already, but let's look at it again. So if kBt times F is essentially the power here, then this will be like 10 to minus 23, 10 to minus 1, and it's in fact about 10 megahertz here, so it's 10 to 7, so we have 10 to minus 10 to minus 17, yes, which is really a measurable thing. So it's let's say the smallest power that we measure is of the order of 1 attowatt or so. So we can resolve quite easily in the measurements. Okay, but let's finish off this part of just looking at the thermometry on these normal systems by a thing which is important, I'm sure, in the future experiments. And this is about the noise of the temperature. So remember, we have been now discussing a kind of a calorimeter, which can be, I mean, in our case, we mainly use just normal metals, standard normal metals. So there's a well-defined small absorber here, which absorbs power. Maybe these microwave photons, which we will discuss during the next hour, or just injecting electrons onto the dot. And this, of course, causes some changes of energy on this dot, and this translates into the changes of effective temperature of this island. Well, but there's a limit how small energy you can measure with this, and this limit is given by equilibrium fluctuations of temperature and energy of this dot. So we all know that in equilibrium we have for electrical current we have the Johnson-Nyquist, or the fluctuation dissipation theorem, which tells that the noise at low frequencies is given by kT times the conductance of your system. So it's something very well known for a long time. But we can have, I told you about the analogy between the heat currents and the electrical currents, and we can write a very similar, I mean, this is something we can derive from the tunnel Hamiltonian for this system, for example, very straightforwardly. We find out that the noise of the heat current in this kind of a basic system here So again, you have the heat capacity, you have the thermal conductance, and the fixed bath temperature. In this case, this T here is the T bath, essentially. So you have that the heat current fluctuates with the, at low frequencies according to this fluctuation dissipation theorem for heat. So again, as before, we see that there's an analogy in the sense that we have now the thermal conductance here instead of the electrical conductance. And the difference here is that in this FDT, what you have is this, there's a T squared instead of T, because we are talking about the energy exchange, not about the charge exchange. Similarly, as we talked about the heat currents in the junctions. So this applies for low frequency noise. So now we can use kind of essentially Ohm's law again for heat current. So that if you have a change in the heat current, I mean, well, just repeating this. So this kind of a fluctuation naturally comes because it's the heat current is composed of, for example, electron phonon collisions of this absorber. So it is, in a sense, it's kind it has noise. It's composed of this kind of elementary events which lead to this noise, and it's, you only need to know the thermal conductance to find this noise. So, but if you combine it now, this heat current with a small temperature difference, we have the linear relation like Ohm's law here via this thermal conductance, and then then the noises, of course, they scale like if you want to find the effective temperature noise at low frequency, then you just divide this by the this conductance squared here, and what you find out is that the temperature essentially fluctuates at with this amount at low frequencies. If you take the larger frequencies into account, I mean, again, remember that this is like a RC circuit. You have some sort of a cutoff frequency there. There's a Lorentzian cutoff for this. This is easy to also derive, but I just tell it to you here. So, so you have, if you have this zero frequency noise, then at finite frequencies it will be damped by the thermal time constant, which is this given by this C over G thermal here, as before. So this is the same as, for example, the electron phonon relaxation rate we had before. So, and if you integrate this noise spectrum here over the frequencies, you get the RMS fluctuations of noise. So if you can measure all the frequencies of this noise, you expect that your temperature will have an RMS fluctuations which are given by kT squared over the heat capacity. So the interesting difference here is that low frequency noise is determined by the thermal conductance again, whereas this RMS noise depends only on the heat capacity, because the shape of the spectrum changes, and that's it. But in our experiment up to now, we have been looking at this, and it is somehow this is the thing that really determines how small energies can you measure in your experiment. So, and these are detectable things. If you just put in numbers and think that you have a very small grain of metal, even at 100 millikelvin, we saw that the cutoff frequencies are low because the electron phonon time constant is low. So we will have fluctuations of temperature which are like few percent. I mean, this goes up at low temperatures. It proportionally goes up, but even at 100 milliK, you expect to have some substantial temperature fluctuations. Here are some preliminary measurements of that. So we have exactly this setup, which is this absorber here, and we measure its temperature by this same thermometer which we have, which I explained to you, this conductance measured in this tank circuit at 600 megahertz driving frequency, and we measure now only up to the bandwidth of 10 kilohertz this noise in this case. So what we have is we have this absorber, it's connected to the bath, we have electron-phonon coupling there, and then we can make, for example, time traces of this temperature. So now at relatively high temperatures, the thermal conductance is determined by this electron-phonon coupling, and if you just bluntly plug this in here, you find out that in, say, the square root of this noise, which is like microkelvin per square root hertz, how much you have noise, it should scale like 1 over the temperature. So here is what we observe at the higher temperatures. So there is some increase of this noise measured from this kind of a spectrum. At the lowest temperature, we see some sort of a roll-off or even decrease of it, and we suspect that this is because there are some other mechanisms of conduction. For example, photons, which we will look at now, which give us maybe a linear dependence on the thermal conductance, and then at low temperatures this should turn over and you should have less noise at lower temperatures. So what does this mean in practice is that if you are now supposed to measure some particles, for example microwave photons, what you expect is that you have this kind of a noise background due to this equilibrium noise, and then as soon as you absorb your particle or your quantum there, then you expect this rise of the temperature and relaxation back to the bath temperature. So if we make the numbers, we see that now to observe microwave photons of say, for example, from the superconducting qubits, which are of the order of 1 Kelvin or half Kelvin, then you need a certain noise equivalent temperature, which is the square root of ST. And in our measurements, we can see that these noise equivalent temperatures that we measure, they are not very far from this prediction of this thermal noise as shown here. And indeed, at the lowest temperatures, the required resolution or required noise equivalent temperature is for seeing a 1 Kelvin photon is shown by these blue lines. Depends a little bit on the model that you use where it goes. So we are expecting that this detector should be able to measure single microwave photons, and this is a kind of a non-invasive measurement. You can monitor the system constantly, and then you should see kind of clicks in the detector every now and then if there is an absorption event. And at the lowest temperatures, I showed you earlier that we can now go down to temperatures 20 millikelvin or even 10 millikelvin. We are expecting that we may have something like a signal-to-noise ratio 10 at this lowest temperatures. So this is just to say where the limits currently are. In fact, it may well turn out that this is not the best detector of microwave photons, because you can imagine, I mean, the ultimate energy resolution of this kind of a detector, let's say delta E, is, I already earlier showed you, it's like this noise of the thermometer times the thermal conductance times the heat capacity of your system. So, okay, so you can think that, okay, if you can make a good thermometer on a system which has weaker smaller heat capacity or weaker coupling to the bath, you may get even much better resolution. And finally, if this noise here is really determined by this fundamental noise, then this goes to a very simple form, which is just written given by this. So if ST is given by this fundamental noise. So in that case, what really determines your energy resolution, you want to make it as small as possible. So is that you make an absorber which has the smallest possible heat capacity, and you operate at the lowest temperature. Usually heat capacity goes down with temperature, so you want to work essentially at very low temperatures with an absorber that has extremely small heat capacity. So currently, I think the graphene Josephson junction detectors are look at the moment the most promising ones, because the graphene has, of course, very, very small heat capacity compared to any metallic absorber. But there is a problem, of course, because in order to come to this limit, you need to have a good thermometer. So we have a good thermometer. We may have problems still with the heat capacity and the thermal conductance there, but still, this is the name of the game. So all these things, they look very promising. So I think one can have a detector for this kind of low temperature quantum systems to look at the absorption of microwave photons in the very near future. Do you have any questions or comments on this part? I now make a shift of the gears a little bit at the moment. All right. So now what I will start to tell you about is about superconducting resonators and qubits as open quantum systems. So we really go to what I showed in the very beginning and now look at it more into detail. And as a kind of a precursor there, I saw also the sort of earlier experiments on quantum heat transport by photons and by electrons as well. And then at the end, I proposed some sort of quantum heat engines and refrigerators that would be based on the superconducting qubits. So let's look at some of the components first here. So we have been looking at LC circuits already before here, and the wonderful thing about superconducting LC circuits is that they have very low dissipation. So you can really model them as LC circuits, and then they are harmonic oscillators because their Hamiltonian is given like this. So you have the charge squared over 2 times the capacitance plus the flux squared over 2 times the inductance of this circuit. So it's a harmonic oscillator where x and p are just given by these 2. So you can quantize this, and I'm not going to do this anyway pedagogically here. I just tell you because this is kind of a thing that we are going to use here. So you have the position and momentum operators, which are related to this ladder operators in the harmonic potential, and these conjugate variables are the charge on the capacitor and the flux through the inductor. And the energy levels are given by this usual harmonic oscillator energies, where now this energy separation is given by the resonance frequency of the LC oscillator. And in these operators here, this prefactor, which is coming from the masses, mass and so on, is just is given by this characteristic impedance, which is L over C. So we will see that in usual circuits, this characteristic impedance is about 50 ohms, because this is what the electrical engineers want usually the circuits to be with. So how are these realized in circuits? So what one does is that one has so one of such resonators is shown here. It's a niobium coplanar wave resonator. So there's a niobium line, superconducting line. It can be also aluminum. Then there's a ground plane around it with a insulating gap in between. So it's a coplanar wave line, and this obeys some sort of simple. It's like a transmission line. So I think you, in some context, you have seen how the transmission line behaves. So essentially, it's a infinite set of infinitesimal inductances and capacitances. And since it's a superconductor, we can ignore the resistance of this line essentially altogether. So typically, if you just terminate this, I mean, you can choose the length of this depending on the frequency you operate. And you talk about lambda or 4 resonators or lambda or 2 resonators. This just leads to either current maximum or voltage maximum at the end of the line. and the particular thing that we do here is that for our experiments, we want to make this like an open system. We want to make this a dissipative system because we are interested in thermodynamics. So instead of having really a very, very high Q resonator, we want to make it a low Q resonator because we connect it to the thermal bath. And the thermal bath for us is this kind of a absorber which I have been talking to you all these days. So if you put this resistor at the end here, you can do a very straightforward calculation, calculate the quality factor of this kind of a resonator, and quality factor is, of course, it's defined as the energy stored in this resonator divided by the energy loss in one cycle times 2 pi. If you do it this way, you really put this on-chip resistor here. You expect that, for example, lambda or 4 resonator has a quality factor which is given by this simple expression here, where this Z infinity is the inductance per unit length divided by capacitance per unit length square root. And this is usually tuned to be 50 ohms because it's something you can achieve. So if you put here some few ohms of resistance, you get quality factors which are of the order of 10, and this is our target in this business. So recently this is really something kind of unconventional. So usually what one measures is that one measures extremely sharp resonances. So for example, the way to measure them is to look at the transmission. I talked to you about S21 measurements. So you put signal in and measure the signal out and look at the transmitted power. And when you are coupling it to the different resonators here, inductively in this case, you have some losses because these resonators here are losing some energy at the resonance. But what we did was that we added this kind of a absorber that I've been talking to you about, a few micrometers long resistor, and it's at the end of this resonator, and we had the reference resonator which did not have it. So if you don't put any such resistor at the end, your typical quality factors are of the order of tens of thousands, but now indeed this resistance gives you a much lower quality factor. So in fact, here is some some measurements of different with different values of this resistance and the quality factors. This is the naive prediction for the transmission line. In fact, it behaves a little bit like an SNS structure in our case because there's some superconductivity induced to this absorber as well, and we got somewhat larger quality factors, but nevertheless we can explain it more or less. So anyways, this is the idea. So we have resonators and they are coupled to heat baths, and now we can, of course, in the experiment we can connect thermometers to measure these baths here. So before we go into any measurements on this, let's just make a small detour about this how this to find if we are in the kind of quantum regime, how the transitions in this kind of a system occur. So suppose we have this kind of LC resonator, and naively let's consider that we have a resistor in parallel here. So as we discussed for the single electron circuits, we have the relevant energy is what you need to consider is the energy of your gadget, which in this case is this one here, and then the work that is done by the source on it. So we had that this Hamiltonian, which in this case is this q squared over 2c plus phi squared over 2l. There is this term which is the work done by the source. So if we had this charge-based systems, then the work was given by q times voltage. But now we have current in Josephson junction. We have the current bias. So then in this case, it's in fact it's phi the flux times current. So so we can write this down as such. So we have the important energy that we consider is this harmonic oscillator energy minus the current that is there. So now let's assume that this resistor here is the only source of the current, and it's inducing noise of the current onto the system. So in this case, we can say that this we have a perturbation, which is this means that we have a perturbation which is phi times delta I, where delta I is the noise produced by this resistive bath here. So in this case, what happens in this in this ladder here, or I mean we'll later go to the qubits. It's a similar thing for the qubit with very minute changes. So this induces, of course, transitions, because if you have noise, the noise induces transitions in the quantum system. So, and we can derive this from the very scratch, but I just remind you that you can find usually the transition rates between states I and j by Fermi golden rule, which you can write down in the form that it is just the matrix element between the between this system operator here times the noise spectrum of this external perturbation at this frequency of the transition, at this level space. So that's the Fermi golden rule. You can do the more. You can write the master equation for the system, and you find this always. So now we know what this operator phi is. It was this ladder operators. I hope I remember the prefactor correctly. Yes. And if we take elements of this, we find, you see, when this operates, I mean, phi j is equal to square root a bar z0 over 2 times j minus 1. This is why it changes it either down or a square root, sorry, plus square root j plus 1 j plus 1. Correct? And if you take now, now we can see that it only connects as usual in harmonic oscillator only the nearest levels. So we find that these, if we take this matrix element squared, we find that Okay, in general we can write it down that that this this gamma I to j is equal to sorry, or this let's no just j ij phi j is okay, and then we find the transition rates in a simple form, of course, because we need to know. Then the other ingredient that we need here is that the noise, the current noise. So I is now here current, not this index, of course. So at this frequency plus omega 0, which is the energy separation of this potential. This in fact is like from fluctuation dissipation theorem. It's emission absorption noise, which is given like h bar omega 0 over 1 minus e to minus beta h bar omega 0, where beta is now the inverse temperature of the resistor. So you know that this I mean this goes to 2 kBt over r when we are in a classical limit, when this temperature gets high. But we use this emission absorption form because this gives us the transition rates as such. So finally, what we see is that the gamma for going one step down is given by j only this term then comes times this, because the matrix element squared, so h bar z0 over 2 and 1 over h bar squared, and then this 2 over r h bar omega 0 over 1 minus e to minus beta h bar omega 0. Okay. And what remains is just j times z0 over r times omega 0 over 1 minus e to minus beta h bar 0. Okay, but this for this lumped LC resonator of this form, this here is 1 over the quality factor. So this is 1 over the Q of this. So we have a relaxation rate which is J times omega 0 over Q times 1 minus e to minus beta h bar omega 0. If temperature is low, this goes to T goes to 0, meaning beta goes to infinity. This goes to J times omega 0 or Q. Similarly, if we go up between the same states, we find just inverting this, taking the opposite frequency here, we find that gamma j minus 1 to j is at finite temperature, it's j over q times omega 0 over e to beta h bar omega 0 minus 1. Positive exponent here, and since this at low temperature increases, it goes to 0 when T goes to 0. So only relaxation at low temperature, of course. Okay, so then there's one important thing which we discussed in the first lecture here, that transition rates up and down are related at finite temperature by detailed balance. So we can see it immediately here because we have the gamma j minus 1 to j divided by gamma j to j minus 1. What remains is just the ratio of these noises, so it's omega 0 over e to beta h bar omega 0 minus 1 divided by the corresponding thing 1 minus e to minus beta h bar omega 0 or omega 0. And of course you can take 1 e to minus beta h bar omega out, and you find that this is exactly e to minus beta h bar omega 0. So this is the detailed balance for the transition rates. Yes. Q is, look, if you have a, so no, this is 1 over Q. So for a parallel LC circuit, the quality factor is R over Z0. If you have infinite resistance, there's no dissipation here because then it's a pure LC oscillator. If it would be a serious LC circuit, it would be the inverse. It would be Z0 over R. Yep. It's time. Okay. Okay, it's time for a break. So I will finish this in the next. Or shall I finish this because it's just a few minutes? So then we can go to the next. So there's one more thing, that what this quality factor is, even in this regime, makes sense in a sense. Maybe this is almost a trivial thing, but what we had is that quality factor, by definition, is the energy divided by energy loss in a cycle times 2 pi. So let's write down what these things are here. Cycle is the natural oscillation period in the well. So we get that this is 2 pi. Let's say that we are in the state J. So the energy is J times h bar omega 0. Okay, there's a plus 1/2, but let's say that we look at kind of in a classical limit. And then we have the energy loss per cycle is this gamma times this times the energy separation. So it is J times, let's take a 0 temperature case. J times omega 0 over Q is the rate at 0 temperature here. Sorry? This is definition, the definition of Q. Yeah? Quality factor is just the definition of quality factor. So let's compare this, what he got, is if it makes sense for this race. So this is a rate that it relaxes times the energy that it loses is h bar omega 0 in each event. And this is repeated at the rate of the oscillation period, which is given by 2 pi on omega 0. And this is exactly Q. So this everything makes good sense. That if you really go to the high levels, this kind of a classical definition of quality factor makes sense for this oscillator. I think we can stop here and then we can go to more experimental things in the next lecture. Yeah, 5 minutes break.
So before we go, important. Secretary say that there's still 10 people who have not paid yet the fee. And it's important to make the payment today before 3 o'clock. So please, those who haven't paid yet, go there and pay. Okay.
Money. Could see.
I was wondering, since finally you want to address the small Q limit in this problem.
Yeah, of course, but
is it, do you really need to quantize, because in the very small Q limit, I would say that the resonator becomes completely classical.
it becomes classical, but we are really in some sort of you will see we are in an intermediate regime.
Okay.
Yeah. There are. So our quality factors are tens typically. Tens.
Yeah, but it, and then, so it means, so you think you still have to, for 10 you still have to quantize?
Well, yes, you can see that there are differences.
It depends on the number, maybe, yes, I know J. Yeah, yes, the problem is that I'm not very familiar with this idea of having a low Q resonator.
Yeah. I mean, nobody is very familiar with this because we really kill the nice resonators.
Because sometimes, the reason why I'm asking you that is that many results
Shall we continue? Okay, so let's go on, and maybe I should say that this is, of course, you can treat it, of course, classically when the resistances are small, so when there's a large damping. But this was kind of educational, and it will relate to what we are doing in the measurements. So, so then one more element, most important element, maybe in this business is a Josephson junction, which is a non-linear. So Josephson junction is a tunnel junction between two superconductors, for example, tunnel junction. And then you can, particularly for tunnel junction, you can write the energy as Ej cosine phi, minus Ej cosine phi. And this, because cosine is, of course, I mean, you don't get the parabola as such, but you get in the lowest, near the bottom of the well, it is a parabola, but then you have the unharmonicity in this potential. And this is important because then you will have non-equidistant levels in the well, and in some cases this unharmonicity, which is determined by the competition of this charging and Josephson terms here, it will make it effectively a two-level system. I don't say much about that. I think that's essentially what I wanted to say about about these systems. I had one slide, but I obviously have lost it now. Okay, it's not maybe very important. So I will jump now to some chronologically to earlier experiments, and I come to the experiments where these arguments are important only a little bit after. So let's go to the topic of so-called quantum heat conductance. So, it is known already from late 80s that if you have a ballistic contact like here for electrons, and you measure the conductance at zero bias as a function of say gate voltage or something, when you open the contact here and you open more and more channels for so let's say that it's a gate voltage, you will see that the electrical conductance here is increasing in steps of 2 squared over h. So this is a known thing and it comes from just a very simple argument, similar to what we did for the tunneling yesterday, that you just have occupied state, unoccupied states, and there's a perfect transmission through this thing. You get that it's 2 e squared over h, this conductance. But much less discussed effect is that also thermal conductance can be quantized. It's not exactly a quantum, but anyways, it has it can assume only certain values. Thermal conductance through, say, for example, in the electrical case, can assume only certain values which are given by multiples of this quantity here. If you take the ratio of these two, you find that they are related by the Wiedemann-Franz law, which we discussed yesterday. So rigorously, you can't call that this is some sort of quantum because temperature appears there, and this is because, of course, in heat transport you always have temperature. But this is something which was proposed on very general arguments by John Pendry already in 1983, some sort of information theoretic arguments, and it is expected to be hold for carriers of arbitrary statistics. So electrons, as we see here, but also for phonons and photons that we will discuss now more in detail. So the earliest experiment on this was done with phonons. So heat transport in ballistic phonon channels, which means that you have, for example, this is the first experiment on this. So what people had was that they experimentally they had kind of a bulk thing which was silicon. Then they had a small membrane of silicon nitride here, which is supported by these ultra narrow legs here. And the only effective heat transport mechanism is by usual phonon conduction through these legs. So what you can do is you can heat this central part up, and you can measure just the thermal conductance, because thermal conductance is, as before, it is Q dot over delta T for small temperature differences. So if you can put, for example, joule power on this central part, you can determine the thermal conductance. These lines that are leading to here were made out of superconductors, so they don't carry heat. What they found out was that this thermal conductance is dropping when the temperature is dropping. Here it is normalized, in fact, by 16 times this thermal conductance quantum. Well, I said 16 because they have 4 legs here, 4 independent legs for thermal transport, and then they claim that they have 4 different modes, 4 different kind of channels of heat transport at low temperatures. This experiment was done already 20 years ago. I think there are not very many demonstrations of it after that. But with electrons, their story is more developed, in fact, with years. So there's an experiment in Paris some years ago, where what was done was pretty much similar thing, but based on electrons. So there was a there's a again a joule heating and of an island, and then there is a quantum point contact which is conducting the heat from this island to the surroundings. And what they could do here, they could measure both the kind of electrical conductance and thermal conductance at the same time, and they find out that they have values of thermal conductance which are multiples of essentially multiples of this thermal conductance quantum. There are several experiments by them after which really confirm this result. But then we should think about one extra mechanism of heat transport. This is by microwave photons. So let's take again one of our absorbers. We have been discussing in and out that it usually is coupled to the phonon bath by electron-phonon coupling. And this was the thing that ceases to be strong at low temperatures. So what else can contribute? So there can be a transport of heat by say electrical noise or microwave photons, whatever you propose it, call the mechanism. So we can there was a theoretical discussion of this in about 15 years ago, and I will go through that in a very brief terms now. And then there are several other theoretical papers and experiments as well. So let's take a very, very simple setup to start with. So we take this, we take 2 resistors. It's like if you heard about Johnson-Nyquist experiment already almost 100 years ago. So this mimics that one. So you have 2 resistors at 2 different temperatures in this case. And then you ask the question, I mean, both of them, of course, produce thermal noise, which we discussed here already. So you can in a circuit terms, you can just assume that it is a series voltage source where you have this where the magnitude of this voltage noise can be written like this. So it's essentially what I had here. So voltage noise which is proportional to frequency and then to the occupation number of the bosonic excitations at certain frequency and certain temperature. So this again, of course, becomes like just the usual thermal noise, 4 kBt times resistance at high temperatures. So now this noise here is then, of course, inducing as current noise in this simple circuit. And and both of them do the same, of course. So, and we can consider these as two independent sources of noise. So the current that this resistor here induces to the circuit at temperature T1 is given by, the noise is given by this voltage noise divided by the total impedance of this circuit squared. And this, of course, is very simple. In this case, it's just the sum of the two resistances. And then the spectral power of this noise at a certain frequency is like I squared R. So it's the power that it is dissipating in this second resistor is R2 times this current noise squared. So after that, it's essentially a one-line calculation to show that the net power between these two resistors, if you assume that they are like both induce this kind of a noise to each other, is the power that one deposits on resistor 2 integrated over all frequencies minus the out-leaking power, which is the opposite expression here. And it's a thing that you can integrate simply analytically, because we had this this kind of a form, and you find out that the power is proportional to the difference in the second powers of the two temperatures. And the prefactor is something very nice. It's just the constants of nature times a small r here. So, and this small r here is kind of a matching or coupling constant, which is determined in this simple circuit by the two values of the resistances. So if the two resistances are equal, then this becomes unity. And in this case, you have the power which is just r equals to 1. You have this power. Now, if you linearize to find the thermal conductance for small temperature difference when these T1 and T2 are close to each other, you find out that the conductance, thermal conductance, is given by this thermal conductance quantum. So this is I think the simplest way of seeing this how this thermal conductance quantum appears in this business. So this exchange energy with a rate. I mean, this is something that even if you have you can put capacitors here. If capacitors are, I mean, you can really have isolating lines. For example, superconducting lines here, or you can put even capacitors in between. If this and this story holds. Of course, if the capacitor is changing the total impedance there much, then of course this is not the case. So an early experiment was done some years ago. So in that experiment there were two of such resistors that we have been discussing. They are here and here. And then in between there were SQUIDS, and SQUIDS are tunable Josephson junctions, where you can say that it's a capacitance in parallel with the inductance, which inductance depends on the magnetic flux. Okay. So in some sense, this is you are tuning this small r, although it's not directly this r, but it is the impedance of this total impedance on this circuit that you are tuning. So it's essentially this guy here which changes now with magnetic flux. So the thermal model of the system now is that you have two resistors. They are both connected somehow to the phonon path, but they are also connected directly by this photonic path. And this is tunable part. So since this, let's say the electron phonon conductance goes like T to power 4. How did it go? Is it EP is proportional to T to 4, as we discussed yesterday. And this photonic part is proportional to T. What happens is that at high temperatures, this is winning, so the system is coupled strongly to the phonons, but at low temperature, this becomes very, very weak, but this coupling remains. So if one does an experiment at the intermediate temperature, changing this inductance by magnetic flux, one can see that there's no, I mean, one of the resistors is heated, and you measure the temperature of that island at the same time. So there's no flux dependence, meaning that this contribution is very weak. But if you go to the lower and lower temperatures, what happens is that this this temperature of this island that you heat starts to get modulated with this flux period of this flux here. And this was matching quite quantitatively to what we would predict in this case. So there is this contribution which takes over at temperatures in these systems at relatively low temperatures. But it means that these two circuits are well matched together. Otherwise, there's much less heat transported. Later on, there were experiments which really confirmed that it's exactly, not exactly, but say within few tenths of percents, the transport between the two resistors is this quantum of thermal conductance, and then a few years ago there was an experiment in another group where they showed that this you can even make a kind of a transmission line or long superconducting line which is even 1 meter long, and the resistors are apart from each other by almost 1 centimeter, and you can still have this quantum of heat conductance transported by photons. Okay, so maybe just very briefly, so one may ask a question, when is this important? So of course this is important when the matching is good, but also it's not important, you can't reach this at say high temperatures, because the important thing is that you have some thermal noise, and all this noise has to be transmitted from one resistor to the other. So you have to have the condition that the thermal frequencies are much lower than the circuit cutoff frequencies, so to say. If the opposite occurs, then you of course don't reach this. And this is the case of, say, all the classical circuits at room temperature. And the reason is that if you take any circuit, you cannot model it just assuming there are purely resistors. You always have to take into account that there are some parasitic components there. And say for capacitances, the minimal you can have is this permittivity times the size of your circuit. That is minimal. And for inductance, it's the permeability times the size of the circuit. So if you make these things, you find that if you are at room temperature, you are never in this limit where you can really transmit this all this noise between the two resistors. Whereas if you are at say cryogenic temperature with small circuits, this is easy to reach. Okay, so let's go now to some more recent stuff, like using this where we can see that this analysis that I did here is in some cases is really necessary. So let's take a more modern setup. Let's take the superconducting qubit and put it between different heat paths. And qubit we can control by either electrical field gate voltages or by magnetic flux. And as I explained in the first lecture on Monday, we can also imagine that we make some work on the qubit by putting, for example, time-dependent flux on it. And we can, I will show at the end that there's a way to really transport heat from cold bath to the hot bath, doing work on the qubit. So how does this thing work? So let's make it just a simple system. So let's say that we have a LC resonator which has some dissipation, or two LC resonators which have dissipation. Now we don't think about driving it in time, we just think about steady state properties of this system. Let's say that this is a hot bath, this is a cold bath. And then what we can do is we can tune the level spacing of this qubit by magnetic flux. So it has these two levels, and the energy separation, this omega 0 here, can be tuned by magnetic flux. So let's take first some kind of a more or less classical picture of the environments. So let's assume that this is a dissipative, not taking this picture, but taking the picture that this is like a dissipative LC resonator, where this resistor produces voltage noise, which then is converted to current noise in this environment here. Okay, and this is inductively coupled to the qubit, this noise. So there is like a Lorentzian. This resistor produces this noise that we discussed up to now, but then this is like a filter here, which tells that there's a noise which is affecting this qubit, and the noise that it produces is Lorentzian filtered. So it affects only at certain frequency on this qubit. So we can still do the same analysis we did here, but we should take into account that this is the type of the spectrum that the environment produces on the two-level system. Doing this consistently and looking at the case when the two resonators are nominally equal, we find that the power, which power is now between the two baths, these are our baths, is given by the simple expression where you have the coupling, and then you have the populations of photons in the two resonators here, these populations, and then you have the Lorentzian cutoff, so Lorentzian filter, which just tells you that the heat is transported only when the qubit level spacing matches with the LC resonator. So this was our initial expectation, rather almost like a boring thing, that you think you have you can tune this, and when you make it to resonance, then the heat can be flowing from hot to the cold bath. So this is the actual circuit. Of course, this is not on the circuit, but it's just for advertisement purposes. So there were these two resonators. They were nominally equal, and then the qubit is in the middle here. It's a standard transpond type qubit with if you don't put our baths there, the lifetimes of these qubits are of the order of 10 microseconds, just some standard qubits. And then instead of a single Josephson junction, it has a SQUID. So two junctions, and then one can apply magnetic flux here to tune the energy spacing of the level spacing of the qubit. And then at both ends we had resistors here. So, and they look like this. So there's this coplanar wave resonator. It's terminated by this aluminum contact here, and then here is the resistor, like we were discussing in previous lecture. So here is the resistor, which makes the quality factor low for this, and which acts as a bath. So it's again a bath of about 1 billion electrons there, and we can measure the temperature of this resistor by usual tunnel junction thermometers. And we can also control the temperature by applying joule power through these junctions. So now the task is just to create a temperature difference and monitor how much power is running through, because once again this temperature difference, we can invert this simple equation. We can tell that the heat current that one of the resistors receives is just if we know the thermal conductance and we measure the temperature rise, that tells us how much is the power that is transmitted from one end to the other. And this we can usually calibrate by applying a joule power here and measuring the temperature difference. So this is how we usually do it. And the results of the experiments were, on one hand, they were not surprising, and on the other case, quite surprising, I would say. Here is again this simple model that I described in words. So we are thinking that we have like the LC resonator, which is damped, and this acts as the environment for the two-level system. And similarly at the other end. So in this case, we would expect this Lorentzian filtering of the heat, and this is exactly what happens in this particular experiment, where the quality factor of the resonator was really low, like 3. So you can see that as a function of the magnetic flux, the power that the cold bath receives. So okay, let me say some more things. So one of the baths, let's say this one, is kept nominally at the bath temperature of the cryostat, whereas we set this to some source temperature, which is usually higher. And then we measure the small changes of this temperature as a function of magnetic flux on this qubit. And this is then we convert it to the power with this simple equation. And we can see that at different temperature biases, we can see that there is a modulation of this power with magnetic flux, and it really corresponds to what we would expect from this simple model with the Lorentzian filtering. So in fact, since what we have is as a function of magnetic flux, we have the energy. So we have the frequency of the LC oscillators is fixed, and then we have the energy of the qubit, which due to this flux dependence of the SQUID is crossing the resonance of the LC oscillator twice in each period, and that's why we see 2 peaks in each flux period here. Okay, so this was not very well. It was nice to see it, but it's not very, very surprising. We could also use the NIS cooling, so we could put a small bias to this. I explained that yesterday. We put a small bias on these junctions here, and we can lower the temperature of this resistor here. And see, these are at the distance of several millimeters, 5 millimeters from each other. And we could cool the other end at 5 millimeters. When we lower the temperature of this below the bath temperature, we can also cool down this one via this photonic coupling here. So this was all very easily explained. And this, it turns out afterwards that this model works out when, let's say, the coupling between the qubit and the resonator is times the quality factor is much smaller than 1, because this is like the ratio of the couplings here, or say here and here. But then we increase the quality factor by about an order of magnitude by just making less resistive this bath. And then the experiment looks very different. So you can see here, this is the similar setup. Again, we measure the power as a function of flux. and you can see that now there are not these Lorentzian peaks, but there are some features in the temperature or in the power which are really look a little bit like experiments that you see usually on qubits. And what we attribute this is that in this case we are in the kind of a true qubit regime, where we can assume that this transmon with two resonators forms one quantum system with its own level structure, and this interacts with the environment, a pure environment, weakly. And this is confirmed by several observations. Well, one observation is that the model that we wrote down it seems to capture it very nicely. But we also could measure the level spectrum of this system when we didn't have these resistors connected, and this is a result from the spectroscopy measurement. So one can see that there are there are these lowest levels. There's avoided crossing there, and this is what comes out when you just simply diagonalize this system here, assuming that the resonators are equal. If they're unequal, there's a little bit of splitting there as well. So that's kind of the competition. So it depends. You are in kind of a local model when the quality factor is very small. But then you go to this global model, like a pure quantum circuit coupled to the environment if the quality factor gets higher. And of course, we are still very, very far from where the qubits are, because we use we have some tens of q equals to 20 or 30 in the best case. So one can model this. I can just quickly show how we did this modeling of this circuit to start with. We started to model it by assuming that we have 3 harmonic oscillators, but we took only the lowest levels of this guy here. And we assumed that there is this, in our case, the transmon qubit is capacitively coupled to the resonators, and then there can be some direct coupling as well. So one can write down the Hamiltonian for that, and then one, of course, you can just write it also in the second quantization, so that you see that there are these coupling terms between A1 refers to the operators of the left resonator, A2 to the right resonator, and B to the qubit, which we also assumed to be a harmonic oscillator in this case. And then we took only into account in this case the basis where maximally one excitation existed in the system. So and this is reasonable, because our operating temperatures were up to maybe 300 milli-K, and this resonator energy separation was somewhat larger. So then when you diagonalize it, you find exactly this simple structure that we had here. And then you find the transition rates with the similar arguments that I had here. Just take the kind of golden rule transition rates, and finally we find that there are some selection rules between these different transitions. So finally we could really get a very nice connection with the experiment. Okay, so then this was a case when we have a fully symmetric system. So we just put the temperature bias and we look at how heat is transported there. But we can also, when should I finish now? Or can I use, I started a bit late, yeah. So let me explain some very recent stuff. There's a hot topic about heat rectification. So what does it mean, heat rectification? So let's take 2 baths, and you have something in between here, which does the rectification. So let's create a temperature bias plus, I mean, this is hot, cold, and you measure the power, and then you make the opposite temperature bias, hot, cold, and you measure this power, reverse power. So usually, I mean, in the system that we had before, we would have got the same answer. Unfortunately, we did not measure that at that time very carefully, so I can't say very much about that setup. But in this case, if the system is symmetric, there's nothing that can make it a rectifier. But there are situations where you can create a thermal rectifier. And the conditions for having a thermal rectifier are that you need to have a nonlinear system here. Harmonic oscillator doesn't do it, or a collection of harmonic oscillators does not do it. And then also you need to have a coupling of this system to the bath, which is not the same to the left and right. These are the two conditions to have thermal rectification. And there's analysis which was done by Segal and Nitzan already more than 10 years ago for a two-level system. And here is my version of the same. So let's look at what happens if you have just a two-level system between two baths, and you find out what is the power between them if the two couplings are unequal. So there's coupling G1 to the left and coupling G2 to the right. Well, we had these transition rates here. Let's apply the same transition rates for this two-level system now, for the two lowest levels of a harmonic oscillator as well. So we have these transition rates to be excited or de-excited induced by bath 1 or 2 written here. Now you can find the steady state population of this two-level system here just by the balance of the rates, where this is the sum of all the rates due to the first and second bath. So this is what keeps the system in some steady state population of the excited state. So for example, if it's equal temperatures, this gives you the usual thermal populations. And then you find that the power is given by this simple expression. This you can derive by some master equation techniques easily, or you can write it directly because it's really really intuitively clear expression. So you have the relaxation rate due to the bath I times the population in this excited state minus the excitation rate due to this bath I times the population in the ground state times the energy that you transfer in this process. So this is the power that goes to the bath I. And if you do this, you find that this system has rectification defined as the ratio of the powers forward and backward, given by this simple expression here. So if if temperature gets low, then this thing beta gets large, and then you see that this becomes unity. So no rectification at low temperature. But when the excited state gets populated, when this beta is higher, then you get the rectification, which is the ratio of the two couplings to the bath. So it's possible to have this rectification in a two-level system. And our preliminary experiment, and you can do the same calculation for putting a harmonic oscillator there, and the rectification disappears for any couplings. So we did a measurement of this in our setup. So this is not the cleanest setup to do this measurement, because now we have like flux-dependent couplings, as you can imagine. So we had a qubit, we had the two unequal resonators, and we put positive temperature, high temperature here, low temperature here, or we reverse the temperature bias. And we measure the flux dependence of the power in the two directions. If you take the ratio of these two and we subtract the minimum, because we have still some problems with the exact calibration, we see that there is clearly a rectification of about 10% in this case, which depends on the flux, because these effective couplings to the two reservoirs depend on the flux due to this, well, you could say this Lorentzian filtering. So it's possible to create a rectifier with this. And as a last thing, for 1 or 2 minutes, I say that what we are really aiming with this device is to make an active refrigerator. So kind of an auto refrigerator with 4-stroke auto refrigerator. And the idea is very simple. So suppose that these are not the same, these resonance frequencies here. What you can do is that you can, in time, you can change the spacing of the qubit here by applying magnetic flux or gate voltage, So you can, in the simplest case, you can just make a sinusoidal drive of the flux here, and you can alternate the coupling of this qubit to the cold path and to the hot path. And if you do it periodically, you can you can obtain in a kind of a steady state, or say quasi-static approximation. You can find what the power is, because it's determined just by the populations of the two baths here. And the answer is that there is a power. This is a power to the cold bath, which is negative, in fact, which is proportional to your driving frequency at low frequencies. Linear, essentially linear. But then when you start to drive it faster, you enter to the regime where you can see some quantum effects, because this qubit at higher frequency starts to make coherent oscillations. So this is something that we are currently working on, but we don't have yet experimental results. So I think since I exceeded time, I stop here.
Any very short question? Okay, so let's do 20 seconds.